application of the verifiable C program logic to your program is symbolic execution based on forward Hoare rules designed for calculational subgoals. It's got a dependently typed maps2 operator for dealing with aggregate types, such as structs, unions, and arrays. And along with that goes sort of a theory of nested structs with field paths. It's got tactics for the introduction and elimination of existential quantifiers. It's got an entailer tactic to simplify entailments. It's got much more. You can see this paper. You can see the PhD thesis of my student Qincheng Cao, who will have his thesis defense 13 days from now, if you're still around. And that's verifiable C. Questions? No. Yes?
Formal methods are basically a bug chasing tool. What happens if you apply it to a buggy program?
Well, hold on. You said formal methods are basically a bug chasing tool, and what happens if you apply it to a buggy program? Let me disagree with the first part. Unsound and incomplete static analyses are called bug finders. Mm-hmm. They're very useful. If they say your program's okay, you have no reason to trust that. But if they say your program has a bug, you have no reason to trust that. But if they say your program has a bug and here's what I think it is, and you look and you say, yes, that is a bug, that's very useful. Mm-hmm. That's bug finding. That's great. You can use Coverity or any one of those tools, and it will improve your industrial processes, and it will find bugs, and you'll fix the bugs, and your program will be less buggy than it was before, and good enough to ship, because it was good enough to ship already. Okay. What we can do is we can verify the absence of bugs. And, you know, it's kind of fun sometimes to take some well-used program from, you know, an open source repo and do verification and find that you can't do the verification because there's an actual bug in the program. You'll get stuck during the verification. But it's even more fun sometimes to verify that the thing is correct, right? To demonstrate a thing that you couldn't demonstrate with a bug finding tool. Now, when I do a verification of a reasonably well engineered and widely used standard thing, let's say like the SHA-256 cryptographic hash function, that's been around for 15 years. People have looked at it. I didn't expect to find any bugs. And there were places where I couldn't prove that it satisfied the specification. And that's because there were bugs in the specification, right? And, you know, if there are bugs, you can't get the proof to go through, and you analyze why, and it's either the specification or the program, or neither, but you can't figure out the proof. That could happen. I don't know, what else would you expect? Question?
I have more a comment from the industry side. As you might know, for C code used in automotive devices, there's a standard which is called MITRA, which is basically the minimum quality standard for C programs. And if you read the standard, an interesting point is that for many of the rules, it says that the rule is actually undecidable. So it is really written in the standard, this rule is undecidable. So that means that you cannot make an automated tool which actually decides if these minimum quality standards of automated C code are actually met. You could only do it with the tools and we'll show you. But the interesting point is you can actually buy NISRA checkers and basically, but you have to read the fine print. The NISRA checker says, well, for all the stuff which is undecided, we do the best job we can to find out if we have these problems or not, but we do not give you any guarantees. And we have basically some manual reviews and to check it. And I mean, this is difficult to say.
Right. So, you know, clearly whether a C program exhibits undefined behavior is undecidable, but that doesn't mean we can't prove it. It just can't be done fully automatically and without assistance from verification engineers. Other questions? Yes?
You compared this technique against like making a bunch of assertions and feeding those assertions into an SMT solver to derive program specifications. Do you feel there are advantages to VST Floyd in terms of expressivity, or like are there things you can express in VST Floyd that you don't believe are expressible just using an SMT solver, like
Right. So the question is comparing VST Floyd to SMT solver-based program verification tools such as, Boogie, Daphne, Framacy, Verifast. And I would say the closest comparable tool is Verifast because it really does work on separation logic for C. And Verifast is a pretty good tool. But the places where VST Floyd has expressivity that you want and that's relevant, I would say the two main things are, first, dealing with sort of higher order programming patterns, as I explained in this lecture. And the second is relating your C program to a functional model that you can then reason about in that same proof assistant. So that you can better integrate reasoning about the properties of your functional model with the refinement of the functional model to the C program. Yes?
Also, a lot of the logical things you wanted aren't going to be supported.
So you're saying a lot of the logical things I wanted aren't going to be supported. So what do you mean by that?
Everything higher order, all that imperative,
Yeah, well, so yeah, you won't have all those quantification over predicates that gives you modularity and function pointers and object systems.
I think, one of the things, I don't have a good sense for this, it seems like every time people build a powerful, do a great proof in a proof assistant, it seems like it needs higher order specs. A year later, somebody comes up with some encoding to first order and builds an SMT-based tool that automates some of those proofs. I actually wonder, in that comparison, if you have any insight about this trend. So we see this with Verity. There's all these Ivy tools like Muley et al. That are highly automated for finding effective invariants and such. And I guess there's just this sort of back and forth arms race. And it seems like the first prototype's always built by the proof system people.
I see. So the question is, in what sense can SMT-based tools catch up to higher order features? And if you think back 10 or 15 years, SMT-based tools were meant for first-order logics. They can't do quantification. Well, now some of them can do some amount of quantification and get it right because, you can always make your logical reasoning system more powerful than it was last year by adding more features. In compiler optimization, right? You can't make a perfect optimizing compiler because that would violate Rice's theorem, which is basically Turing's incompleteness theorem. But you can make a better one than you had last year by adding more code that does more safe reasoning. And so you can take any system, whether it's the entailer tactic of Floyd or the encoding into SMT problems that an SMT solver uses to make a more powerful reasoning system than you had before. So, it's not entirely clear whether, in the end, the systems that we want to use are sort of tactical proof automation in higher order logic, enhanced by lots of proof automation, or more and more expressive encodings into SMT. Who knows? Question?
Does VST handle 64-bit CompCert or like x86?
Does VST handle 64-bit CompCert? So about 2 years ago, CompCert was generalized from being just a 32-bit C compiler to being a 32-bit C compiler and a 64-bit C compiler. The verifiable C core program logic is proof sound for both the 32-bit and the 64-bit versions. And one of the projects near the top of the stack is to extend the Floyd proof automation to get right the 64-bit mode as well. So I expect that will happen within a year. And that's an invariant. Yes?
If you use the claim spec of another function when proving a function to be correct, what keeps things well-founded?
Right. So when I get to use the specification of some function in proving this function correct, or maybe even in a recursive call, the specification that I assumed about this function I get to use in the proof of the function, and that seems circular. So what keeps this well-founded? And the answer is the step-indexed program logic. The later operator of the program logic allows you to justify the well-foundedness of reasoning that when you make your recursive call, at that point, there are fewer execution steps left to execute in the program. And it's really an induction on how many execution steps remain. So we start, even for infinite loop program, even for programs that you don't expect to ever terminate, you can still prove them safe and partially correct by saying, okay, let's arbitrarily pick a number after which that number of steps, after that, I won't care whether it's correct or not. And then prove that by induction of the decreasing number of steps remaining to execute before I don't care anymore, that the program is correct. And that justifies this circular-looking assumption. And the whole proof of soundness is done by over sort of an arbitrary number. And then you can pick a number that's equal to the number of Planck times left before the universe has decayed to all iron, if you like. And after that, I don't guarantee the safety of your program. Yes?
I saw in the lemma for the node that there was a later in the precondition.
Yes.
That didn't show up when you went through the proofs using the node.
Right. So
like that is automated?
Yes. Here, where is the later? Yes, there's a later right here in the precondition. And that says the precondition required for doing load is that it's approximately true that this is the case. But when you're calling the load, you know that it is true. So P implies later P, always. That's just a fundamental fact about later. And therefore, the Floyd proof automation system can always easily remove these laters when they occur in the precondition of a rule you're about to use. The user never needs to see a later unless doing something really fancy with making new rules for reasoning about higher order functions. One more question, and I think we should take the break, and there will be another Verifiable C lecture. So, or
just a comment back to what Zach said, sort of that SMT solvers and automatic technologies can, in principle, catch up. I think there's also a price that they have to pay for that, and that is in the kind of encoding that they do from the expressive assertions that we have here into SMT formulas. That really increases the complexity of the tools, and it's not always easy to see that that's actually soundness preserving, whereas we work here in a improver and have that property, and we're moreover linked directly to the operational semantics of C-Lite of concept. So there is a soundness or trust gap that these tools typically have.
I think it's actually a really good point that doesn't get highlighted in the papers that show these reductions. The reductions are neat, people get excited about them, but they're all on paper. And that should make us worried.
Yeah, and if you wanted to, I mean, even if you did just have them sort of return witnesses in order to check them, you would have to re-implement that entire semantic justification.
So maybe one way to look at it is that there's always a place for the higher order logic because somebody's got to verify the reductions at least.
yeah. So there will be one more lecture on Verifiable C, and I think we should continue this discussion tomorrow.